stress, it is the intensity of force inside the solid. It is also defined as the ratio of force applied to the resisting area. It is denoted as sigma, which is equal to the quotient of applied force and the cross-sectional area. Units in standard system is MP. Three types of simple stress includes normal stress, shearing stress, and bearing stress. In normal stress, the applied force is perpendicular to the resisting area. It has several types which include tensile stress. In this case, the force pulls the member of the body and the material is being stretched. Another type is compressive stress. The force pushes the member of the body and the material is being squeezed. The figure shows the difference between tensile and compressive stress.
Visualizing all the types of stress, let's first have a sample problem for normal stress. So the problem is a hollow circular post ABC supports the load P1, which is 16 kN acting at the top. The second load P2 is uniformly distributed around the cap plate B. The diameters and thicknesses of the upper and lower parts of the post are DAB equals 30 mm, PAB equals 12 mm, DBC equals 60 mm, and PBC equals 9 mm respectively. The lower part of the post must have the same compressive stress as the upper part. What is the required magnitude of the load P2? As shown in the figure, it is a hollow cylindrical post, and so the resisting area is an annulus. Area of an annulus is equal to the area of the bigger circle minus the area of the smaller circle. For the acting force, post AB receives load P1 only, while post BC receives both P1 and P2. Now, solving for the stress AB, it is equal to the load P1 over the resisting area. Substituting all the values, stress in AB is equal to 16,000 Newton divided by pi over 4 times the quantity 30 mm squared minus the square root of the quantity 30 mm minus 2 times 12 mm. And stress in AB is equal to 23.58 megapascal. It is mentioned in the problem that the compressive stress in post AB and post PC must be equal. Using this condition, load P2 can be solved. Stress in BC is equal to the quantity P1 plus P2 divided by the resisting area BC. So P2 is equal to the quantity stress BC minus resisting area BC minus load P1. Substituting all the values, load P2 is equal to 18,000 Newton or 18 kilonewtons.
Shearing stress is caused by the forces parallel to the resisting area, and it is computed by the shearing force over the surface area. If the material is under double shear, based on the formula, you're just going to multiply the area by 2.
Another type of simple stress is bearing stress, in which it is a contact pressure between two separate bodies. It differs from compressive stress because compressive stress is the internal stress caused by a compressive force. It is denoted by sigma sub mi, which is equal to the compressive force denoted by P sub B over the characteristic area perpendicular to it denoted by A sub B.
Now let's have a bearing stress sample problem. A 7/8" diameter ball having a diameter at the root of the threads of 0.731 inch is used to fasten two timbers together as shown in figure P-129. The nut is tightened to cause a tensile stress of 18 psi in the ball. Compute the shearing stress in the head of the ball and in the threads. Also determine the outside diameter of the washers if their inside diameter is 9/8 inch and the bearing stress is limited to 800 psi.
Based on the
solve for the shearing stress in the head of the board, we must solve first the tensile force on the board, which is equal to the tensile stress times its area, where the tensile stress is equal to 18 psi and the area is equal to 1/4 pi times 7/8 squared. The tensile force is equal to 10.8 newtons. Now for the shearing stress, which is equal to the tensile force over its area, where the tensile force is equal to 10.82 and the area is pi times 7/8 times 1/2, the shearing stress in the head of the board is equal to 7.872 psi. For the shearing stress in the threads, tensile force over the area of the threads, where the area is equal to pi times 0.731 times 5/8, the shearing stress in the threads is equal to 7.53 psi. For the outside diameter of the washer, the formula we are going to use is the force equal to bearing stress times its area. The outside diameter is equal to 4.3 inch.
Our next problem is on bearing stress. So for our problem, the two wooden boards shown below are connected by 0.5 inch diameter. Washers are installed under the head of the board and the undernut. The washer dimensions are outer diameter is equal to 2 inches and inner diameter is equal to 5/8 inch. The nut is a 1/2 inch zinc finish grade 8 inch hex nut. The nut is tightened to cause a tensile stress of 1000 psi in the board. Determine the bearing stress between the washer and the board. Given in this problem, when we tie this board, there will be an equivalent stress that will act between the washer and the board. In solving problems in statistics, it is important first to determine an element to consider and to perform the equilibrium equation. So in this problem, the element that we need to consider is shown in the figure. The stress applied in the board is 9,000 psi, and this force or this stress is related with the stress that is acting between the washer and the board. First, we need to know the area in which the 9,000 psi stress from the board is acting. We have area is equal to pi/4 quantity outer diameter squared minus inner diameter squared. We get the value is equal to 2.835 square inch. Second, we will also determine the area in which the unknown stress is acting. We have the formula A is equal to pi/4 diameter squared. We get the value equals to 0.196 square inch. From the area we obtained, we get the equivalent force from the 9,000 psi stress, and we get the force equals to 1,764 pounds. Using the stress formula F/2. Considering the equilibrium in Y, we will know that this force is equivalent with the force acting between the washer and the board. And from that force, we will determine the stress from the washer and the board using the stress equation force over area. We have the force equals to 1,764 pounds. We divided it by the area of 2.835 square inch, and we will get the equivalent stress equals to 622.22 psi.
Most of the time, we use thin-walled pressure vessels to contain fluids. One common example of a thin-walled pressure vessel is a cylinder. So let's suppose this water bottle is a perfect cylinder. This bottle can rupture in this direction, the longitudinal direction, and this direction, the tangential direction. The longitudinal direction, the stress in there is given by the formula stress is equals to the gauge pressure
the pressure inside minus the pressure outside, that's the gauge pressure, times the diameter divided by 2 times the thickness of this thin-walled pressure vessel. On the other hand, the tangential stress is given by the same gauge pressure times the diameter, but you will divide it by 4 times the thickness. So as you can see, the longitudinal stress is less than the tangential stress, and thus in design, it controls the maximum pressure that can be contained in a cylindrical pressure vessel. Pressure vessel is also a common example of thin-walled pressure vessels. The stress is given by the gauge pressure times the diameter of the sphere divided by 4 times the thickness of the wall of the sphere. Commonly, we can see it in balloons. As we all know, there is a limit in how much pressure we could put inside the balloon before it pops. The pressure is controlled by the stress formula given a while ago.
An example of problem solving for the thin-walled pressure vessels is a water tank is 8 meter in diameter and 12 meter high. If the tank is to be completely filled, first, determine the tangential force on the tank. Second, determine the minimum thickness of the tank, rating the stress is then limited to 40 megapascal. For the first part, considering the tangential force in the tank, where F is equal to W times H times A, given 9,810 times 12 times 8 times 0.001, you can have the force of 941.76 Newton. Considering the inward and the outward force in the tank, you can have 2P is equals to F, and we can have P as 470.88 Newtons. By getting the minimum thickness of the tank, by the formula stress equals to force over area, 40 is equals to 470.88 over E times 1, you can derive it and have a thickness of 11.77 millimeter.